Okay, in this very last video in this module, we are going to go through how we can connect the Maxwell relations and this really handy mnemonic called the thermo square. So this is not in your textbook, it's something that I learned in graduate school, and I hope that it serves you as well as it has served me. So again, I introduced this idea of the Maxwell relations in the last video, second derivatives of the four thermodynamic potentials with respect to their natural variables. And as it turns out, being able to work our way through these relationships is handy. So here is a mnemonic that's going to help us remember all those relationships. As promised, the thermo square. So the one thing that we do have to memorize is getting the correct order of these letters and drawing these arrows in this way. So when I learned this, we learned it as verified analysis of thermodynamic understanding gives solutions to hard problems. I encourage you to come up with your own acronym, something that's going to help you out. In the past couple of years, students have called this VAT-UG-SHIP, and that has stuck pretty well with me. VAT-UG-SHIP. And then we draw the arrows from S to T and P to V. Okay, here is how we use this thing. So let's suppose we want to first start with enthalpy and get our correct thermodynamic relationships and Maxwell relations for enthalpy. So we've circled enthalpy, and now I'm going to draw a little horseshoe thingy around the thermo square with U in the very bottom trough of this little horseshoe. Okay. So what we learn is H is sandwiched between S and P. So that tells me that H is a function of S and P. Lovely. And because H is a state function, that means changing the order of operations should not matter. So we can now recognize we're dealing with second derivative of H with respect to S and P. Okay, lovely. And now we're going to use these arrows in this trough to work out this Maxwell relation. So I'm going to start with the constant S arrow, and I'm going to travel up, and that takes me to the T. And now I can write partial of T by partial of P at constant S. Okay, so that is one of our Maxwell relations. So we went H, and then I went over to the S, traveled up, partial of T by partial of P at constant S. Now we're going to do the opposite side. We'll go to the constant P arrow, and we'll travel up, and we'll now say that that's the partial of V by the partial of S at constant P. So partial V, partial S at constant P. Lovely. And that's our first Maxwell relation derived from the thermo square. Okay, let's do internal energy. So there it is. There's U, internal energy. And now I'm going to draw a horseshoe again, but this time I'm going to tip the horseshoe on its side. Remember, keeping U like in that bottom little trough. So now we can see U is sandwiched between V and S. So that gives us our natural variables of U. And once again, because this is a state function, we can change the order of derivatives with respect to S and V, and it won't change the outcome. So now let's first play with the constant S arrow and travel with the arrow. Okay. So now that becomes partial of T over the partial of V at constant S. And now something different is going to happen. So we go to the constant V arrow, and now we can see we're traveling against it, right? So because we're traveling against the arrow, that's going to give us a negative sign. That's how this mnemonic works. And then now that's partial of P by partial of S at constant V. So partial of P by partial of S, all at constant V. And there we go. There's our second Maxwell relation. Okay. So we can finish these off All right, so now let's do the Helmholtz free energy. So we'll draw our little horseshoe the same way. Now this time rotated again, keeping A at the bottom of the horseshoe. And now we can see A is a function of V and T. It's smashed between the V and T. And now looking at its Maxwell relation, second derivative of A with respect to the partial derivative of V and the partial derivative of T. And now you can see we're going to travel against the arrow both times. So I'm going to say negative sign, and I will go against the V. So now that's going to be the partial of P by the partial of T, all at constant V. And then now we'll have another negative sign because we're traveling against the arrow. So we'll travel against the arrow from T all the way to S. And now that's, oh wait, what did I do here? Partial of V, oh yeah, PT at constant V. Okay, good. So I was about to do it against the horseshoe. Never mind. Let's keep going with this. So partial of S with respect to partial of V at constant T. So SVT. Okay, checking to make sure I didn't mess anything up. Yes. And because this is like a negative situation, we could also write this as negative in front of the derivative in the first place, and then write both of these as their positive counterpoints. Okay, so either one of those is correct. And then finally, we're ready to do our Gibbs free energy Maxwell relation. So we circled Gibbs. We're going to draw the horseshoe again, this time rotated another 90 degrees. We can see G is a function of T and P, which, by the way, this is why we love the Gibbs free energy in chemistry, because its natural variables are temperature and pressure, two things that we readily manipulate in a chemistry laboratory. Okay, so looking at its Maxwell relation with temperature and pressure, we'll start with the pressure arrow and we'll travel over to volume. So that's dV by dt at constant P by dt at constant P. And then now we'll go to the temperature arrow and we're traveling against it. So that's a negative sign. So that's negative partial of S by partial of P, all at constant T. Lovely. So that is how we can quickly regurgitate our Maxwell relations. Additionally, we can also use the thermo square to help us with our criteria for spontaneity, right? So recall we looked at G, that it's sandwiched between T and P, and there we go. We can see dG at constant T and P must be less than 0 for spontaneous process. We can look at A and see it's sandwiched between V and T, and there we can see that relationship for spontaneity. The dA at constant T and V must be less than 0 for spontaneous process. We see H sandwiched between S and P, and of course dH at constant S and P must be less than 0 for a spontaneous process. And U is sandwiched between S and V, so we can see du at constant S and V must be less than 0. And now when we look at our two spontaneity criteria for entropy, we can see there's two of them. One in which we have S with constant H and constant P that we can see there, right? So S with constant H and P must be greater than or equal to 0. And then again, S, and here we can see with constant U and V must be greater than or equal to 0. So there's several ways we can use this thermo square to help us work through all of these relationships. And we'll definitely work through this at our live lecture, but I think your ability to quickly draw up the thermo square and work through this is going to help you out a lot, especially in our ACS exam. Okay, folks, that's it for this module. I'll see you in our live lecture.